Good morning. We are going to start on lecture number 16 of electric drives course. We had already seen the conventional ways of controlling the speed of a DC motor. So we had looked at different schemes that are adopted for controlling the speed of a separately excited DC motor as well as a series motor. So we'll be working out one problem on series motor today. But before we really start working out the problem, let me now start with rectifier fed DC motor drives. So after that, we will be looking at chopper fed DC motor drives as well. But rectifier fed DC motor itself will consist of many topics. So let me try to write down those things, what all we'll be looking at. First of all, we'll be looking at single phase rectifier fed DC motor drive as well as three phase rectifier fed DC motor drive. And in single phase itself, we will be looking at uncontrolled, which we may not dwell for too long, then fully controlled and semi-controlled. So all three of them we'll be looking at. The same thing holds good as far as three-phase as well. Even in three-phase, we'll be looking at uncontrolled, fully controlled, as well as semi-controlled. Okay. But after that, we should be looking at dual converter. So how dual converter can be used for achieving 4-quadrant operation in a DC motor drive, that we'll be looking at. After looking at all these things with respect to separately excited DC motor drive, finally, we need to look at series motor drive as well. So these are the different topics we'll be looking at when we are discussing rectifier fed DC motor drive. So the configuration, what we are looking at. So let me first of all look at rectifier fed separately excited DC motor drive. So what we are considering when we are analyzing the separately excited DC motor drive fed by a rectifier is, so we are going to have all 4 devices in the single phase circuit as diode if we are talking about uncontrolled rectifier, which is actually feeding a separately excited DC motor. But this generally is not employed very commonly because this is not going to give you the flexibility of varying the armature voltage that is being applied to this particular motor drive. So that is the reason generally we will go in for either fully controlled or semi-controlled, depending upon whether we want only 1-quadrant operation or 2-quadrant operation. So this is typically the DC motor drive we are looking at. We are initially going to assume that the field current, what is being sent, that is going to be a constant. So the field current is going to be a constant in this particular DC motor drive. So IF, I am not going to vary. And the device, let me number like this. This is going to be T1, this is going to be T2, this is T3, and this is T4. And this is going to be Vm sine omega t. This is going to be the source. And during positive half cycle, this is going to be plus and this is going to be minus. Let me call this point as A and this point as B. So I'm going to first of all start with single phase fully controlled rectifier fed separately excited DC motor drive. And let me call this terminal as A1 and this terminal as A2. So we are going to make certain assumptions before we start the analysis. So let me first of all state those assumptions. So the first assumption that we are going to make is that the devices are ideal, which means the moment you reverse bias them and then you are going to reduce the current also, the device is going to turn off immediately. Similarly, the moment you give a gate pulse, immediately it is going to turn on. So T on and T off are negligible. That is the on duration and off duration that is taken up by the device for recombination and so on. That is negligibly small. The second one that we are going to assume is RA and LA are constants for a given motor drive. They are not going to change with temperature or time or something like that. If you are going to run it for too long, in all probability, the motor winding will get a little heated up, but we are not going to consider any change in RA and LA. The third assumption that we are going to make is the source is ideal. That means there is no source reactance or source resistance. So we are not going to consider commutation overlap. So the commutation overlap does not exist. So let me write this as no commutation overlap. So the commutation overlap is not being considered. The fourth one that we are going to assume is the time constant. The inertia of the motor is high. Inertia is high. So I am going to assume that mechanical time constant is much higher than 20 millisecond. So the speed is not going to change within one cycle duration of this 50 Hertz power supply. So which means we are going to assume that EB speed is a constant that is not going to change much within 20 millisecond. So this is within 20 millisecond. So we are not going to really have EB variation because we are assuming field excitation is also a constant. So EB, which is K phi omega, this will be also a constant within 20 milliseconds. That's what we are trying to say. So these are going to be the assumptions we take up. Now, one more thing we might have to consider is which devices conduct. For deciding that, first of all, we have to understand that, first of all, the device has to be forward biased. Device should be forward biased and gate pulse should be present. So only if these two conditions are satisfied, the device is going to conduct. Otherwise, it's not going to conduct. That's what we are trying to say. So we'll have to check under what condition the devices are going to be forward biased. So if I am considering T1 and T4, in positive half cycle, we are going to have this to be positive and this to be negative. So this is negative. The point B is negative. So during positive half cycle, if I try to write what is the situation during positive half cycle, we are going to have point A is positive and point B is negative. So because of which we are going to have actually device number T1 as well as device number T4, because T4's cathode is negative and T1's anode is positive, whereas T2's cathode is positive in positive half cycle. So we can say directly T1 and T4 will be forward biased. But this is true provided I'm going to have a back EMF here. That back EMF is going to have plus here and minus here, and that is also going to come up here. So if I am talking about the current is not flowing already and you're trying to fire T1 and T4, there will be a tug of war between what is the supply voltage and what is the back EMF. Supply voltage is coming here, back EMF is coming here. So forward T1 and T4 will be forward biased provided supply voltage is greater than back EMF. And this is true if there is no current flowing already through the armature. So similarly, I should say T2 and T3. T2 and T3 will be forward biased provided supply voltage is greater than EB. What I mean is supply voltage magnitude is greater than EB during negative half cycle. But if the current is already flowing, if there had been a current, so let us say previously there had been a current and I am trying to fire now T1 and T4. So the current would have flown actually through T3, it would have flown through the DC motor drive and it would have returned through T2. So it is going to return through this particular terminal. So it will return through this and it would have flown inside through this. So from B, the current would have flown to through T3 through the motor drive and then T2 and back to the supply. So T3 and T2, both of them are going to work like short circuit. So I can show it as though this is a short circuit. If this is a short circuit, in that case, this point which we call as B, this point we are calling as B. This point B is going to be reflected here as well, and this is going to be B. So as long as VAB is positive, T1 will be positive, provided there is already some current flowing through the motor drive. So if the current is flowing through the motor drive, I will assume that T2 and T3 must have been conducting because I'm trying to fire T1 and T4. So if I am firing T1 and T4 at that point, I will have T1 having VT1. If I try to look at the voltage, that will be same as VAB. So VAB is supply voltage. So if VAB is positive, then I am going to have VT1 getting forward biased, provided there is a conduction already existing. So VAB is same as supply voltage. So in positive half cycle, we are going to have T1 and T4 always ready to get fired. The same way in negative half cycle, we will have T2 and T3 ready to get fired, provided there is continuous conduction. So we are going to say that in continuous conduction, if there is continuous current, in that case, we can say T1 and T4 are ready to be fired during positive half cycle. Whereas T2 and T3 are ready to be fired during negative half cycle. So this is only in continuous conduction. Whereas if the current is discontinuous, if it has, hit 0, in that case, we will have to compare supply voltage and EB have to be compared with each other before deciding whether a particular device can be fired or not. So just to reiterate, let me draw the circuit again. So this is single phase, fully controlled converter feeding a separately excited DC motor. So this is feeding a separately excited DC motor. So if we are looking at this, let me draw the circuit once again. So this is the circuit. We are going to have the sinusoidal supply voltage here, and I'm going to call this point as A and this point as B. And I'm going to have one device here, which is T1, one more device here, which is T2. Then I'm going to have T3 and I'm going to have T4. So this is getting connected here and this is getting connected here. And from here, I'm going to have the DC motor drive connected to this point. Okay, now this is the field. So this is going to be IF, which is flowing through this separately excited motor's field. Now, if I'm going to assume that T1 and T4 are conducting, under that condition, point A is going to be connected here. And point B is going to be connected here when T1 and T4 are conducting. When I'm talking about T1 and T4 conducting. So under that condition, if I try to write the equation, what is really being applied to the DC motor drive, I should say Vm sine omega t equal to R1, RA IA plus LA DIA by dt plus EB. Whatever is the back EMF. If I assume that maybe the motor is rotating in a particular direction and it is giving a voltage of EB as the back EMF. And this is going to be the equation what I have for this particular case. Okay. Now, I can say that Vm sine omega t, let me call this as VA, armature voltage, instantaneous voltage, what is appearing across the armature terminal. So I can say VA minus EB should be equal to RAIA plus LADIA by dt. If I assume that RA is going to be really small, I can probably neglect it. So VA minus EB is going to decide whether I'm going to have an increase in the armature current or decrease in the armature current. So IA will reach its maximum value when PA is equal to EB. When both of them are equal to each other, then I'm going to have the armature current reaching its maximum value. So with this in mind, let's try to draw the waveform. So the waveform, let me draw like this. So this is going to be the sinusoidal voltage that I'm applying. So this is omega t. And I'm going to fire probably this particular device T1 and T4 at alpha. So I'm going to say that here I'm going to fire T1 and T4. They are going to be fired at alpha. Whereas this is pi plus alpha. And let me draw this rectified voltage for the negative half cycle also somewhat like this. So this is going to be pi plus alpha. And this is where I'm going to fire T2 and T3 because symmetrically we will fire both the devices, one at alpha, one pair at alpha, the other pair at pi plus alpha. So if I say that the back EMF is going to be somewhere here. So this is going to be the back EMF because it is a constant value and it is opposing the applied voltage. So this is how it is. Now, we are going to have initially T1 and T4 conducting. So I'm going to have this entire voltage appearing as the voltage across the armature. And T1 and T4 are going to continue to conduct until this point. So I'm going to have this also as the voltage that is appearing across the armature. Now, after that, I'm going to have this as the voltage that is appearing. So I should show this as the voltage that is appearing. So this voltage repeatedly is appearing across the motor drives armature every half cycle. So half cycle after half cycle, I'm going to get a similar voltage. So if I want to know what is the average voltage, then I have to write this as from alpha to pi plus alpha. I have to write Vm sine omega t d omega t, and this should be averaged over half a cycle because we are only integrating over half a cycle. So we had started from alpha and we are going until pi plus alpha. So that is half a cycle. So this will come out to be 2 Vm by pi cos alpha. So depending upon what is the value of alpha, the average voltage is going to change. This you must have studied in power electronics course itself. Now, if I am looking at this expression, that is LA DIA by dt is positive if VA is greater than EB, and it will be negative if VA is less than EB. So under this condition where you are firing, actually, VA seems to be slightly smaller because this is where VA is. It is slightly smaller than EB. So there may be a slight reduction in the current, then it will start increasing. So I should show as though there is a slight reduction in the current and then it is going to start increasing and it will reach maximum when VA and EB are equal to each other. So it will reach a maximum, then it will again come down. Then again it will reach a maximum here, it will come down. So if I try to draw the armature current, the armature current has to be drawn in such a manner that from roughly from here to here, it is going to increase and then it will decrease. Then again, it will increase, decrease, and so on. So this is going to be IA, whatever is the current that is flowing through the motor drive. And if there is higher and higher value of LA, then correspondingly, this will become, it will become much more like a straight line or an average value. It will be, the ripples will be decreased tremendously. That's what I mean. So if I look at the average value for this may be somewhat like this. This is the average value, IA average value. But the ripples are there because your voltage is increasing and decreasing. So this is Vm sine omega t. And what I have shown as the blue color shaded area is VA. And what I have shown in green color, this is going to be IA. And of course, this is EB. Okay. Now, if I try to look at what kind of current is flowing here, when I am having T1 and T4 conducting, T1 and T4 are carrying a positive current which is having the same direction as that of the armature current itself. Whereas when T3 and T4 are conducting, we are going to have the current flowing like this and then flowing through the armature. So when T2 and T3 are conducting, the armature current and the supply current are going to be in opposite sense. So that is the reason why if I draw the actual current waveform, how it looks like when my devices are conducting, right? I am going to have during this portion, the current is exactly going to follow whatever is the armature current. And when I have T2 and T3 conducting, I am going to have the current somewhat like this. So this is when T1 and T4 are conducting. And this is where T2 and T3 are conducting. So you would see that the armature current direction is going to be reverse when I am looking at T2 and T3 conducting as compared to the supply current. The supply current and the armature current are going to be in opposite sense. So if I say that the average value of voltage is 2 Vm by pi cos alpha, and LA dIA by dt, the average value is going to be 0 because over one half cycle itself, the inductance will absorb energy during IA increasing and it will return energy during IA decreasing. This is the way it is going to be. So the net voltage drop across LA over half a cycle is equal to 0. So I should be able to write this as VA equal to EB plus IARA on an average basis. This is the averaged equation. So I should be able to write this as 2 Vm by pi cos alpha equal to EB. Rather, I can take this IARA to the other side. So I can write minus IARA equal to EB, which is K phi omega. So I should be able to write this as 2 Vm by pi K phi cos alpha minus TE divided by K phi whole square multiplied by RA equal to omega. So this is actually the speed torque expression corresponding to single phase fully controlled rectifier fed separately excited DC motor drive. Now what we have derived, this is steady state or average equation. So this is going to be steady state speed torque characteristics or variation. Whereas if I want to really know the transient equations for the motor drive, I should write when alpha is between 0 and pi, or I should say when omega t is between 0 and pi. In fact, not even 0, alpha and pi, because I'm going to fire the devices T1 and T4 only at alpha, not before that. This is alpha. So when omega t is between alpha and pi, under that condition, I can write Vm sine omega t equal to EB plus IARA plus LA DIA by dt. And if I'm assuming continuous conduction, these two are going to conduct until pi plus alpha, T1 and T4. So when alpha lies between omega t lies between alpha and pi plus alpha, this particular equation will be valid. So I should be able to write the solution for this. So in fact, I can bring this EB to the other side. So let me write this as Vm sine omega t minus EB equal to IA RA plus LA DIA by dt. So there will be two components to the actual forced solution or forced response. One will correspond to Vm sine omega t. So when you give a sinusoidal supply, I'm going to have Ia of t to be Vm divided by Z sine of omega t minus phi. So where I'm going to have Z to be RA square plus omega square LA square square root. And phi is going to be tan inverse of omega LA divided by RA. So this is like any other sinusoidal AC circuit with RL. So this is how it is defined. The next one is going to be the forced solution, which is corresponding to EB component. So that is going to be minus EB by RA. And the third component is actually the transient component, which we have to write as K1, which is some constant multiplied by e power minus t by tau A. So this is going to die down slowly. So this is the transient component. So I should define what is tau A. Tau A is the armature time circuit time constant, which is LA by RA. So this is the kind of equation we are going to get for IA of t. So this is the expression for IA of t. Now K1 can be solved for by substituting initial condition or initial and final condition. So initial condition in this particular case, I can say whatever was the current value that was starting at pi plus alpha and alpha, both of them have to be equal to each other. So under steady state, once the machine has reached, the drive has reached steady state, we can say basically we are going to have IA of alpha is going to be equal to IA of pi plus alpha. So if we substitute this condition, we can solve for K1. So by solving for K1, we will get a closed form expression for IA of t. So this IA of t is corresponding to continuous conduction provided we have really got the value of K1 solved for from this particular initial and final condition. So this is a pretty long expression, and that is the reason why rectifier fed DC motor drive, it's not going to be very easy for us to determine the exact value of speed for a given torque if we are given a firing angle. If we are given a firing angle and we know for sure that the machine is drawing continuous current, then it is easier to determine because you are going to have basically 2 Vm by pi cos alpha, which is Va minus Ia Ra equal to Eb. And obviously we will be able to solve for omega from this expression. So for continuous conduction zone, if I try to look at the DC motor drive speed torque characteristics, this is going to be Te and this is going to be omega. So we are going to have probably this as corresponding to alpha equal to 0 degree. and this may correspond to alpha equal to 15 degrees. This may correspond to alpha equal to 30. This may be for alpha equal to 60 and so on. Please note, I am really not joining these characteristics to the speed axis because if the torque is much lower, so the torque is much lower at this point. If torque is lower, IA is small. If IA is small, we may not be able to have continuous conduction. Unless the current is larger, you are not going to have continuous conduction. So at lower torque values, there will be discontinuous conduction. So this particular equation, what we wrote, that 2Vm by pi cos alpha as the expression, this will not be valid. This is not valid when during discontinuous IA. If I'm going to have discontinuous IA, I'm not going to have this expression valid. And that is the reason why I cannot really directly apply this particular expression when calculating the speed and torque. So I cannot apply this particular expression under discontinuous conduction. That is the reason why for very low torque values, I have still not joined these characteristics. This portion I have left really hanging. So that we need to fill in when we talk about discontinuous conduction. So we'll talk about discontinuous conduction in the next lecture class. But in the meanwhile, let me try to work out one problem. So one numerical example on series motor. So we are going to have one numerical example on series motor. So let me read out the problem statement. A 4-pole DC series motor is driving a fan while taking 60 ampere from a 220 volts supply. So driving a fan at 2000 RPM. Actually, the speed is going to be 2000 RPM and current is 60 ampere and supply is 220 volts. Okay, so this is what is being given. Now, what is being asked is the field coil the field coils, 4 of them, are connected in series at 2000 RPM. If the field coils are now connected in 2 parallel groups of 2 in series, then calculate the speed and the current. Neglect field and armature resistances and assume that VA is a constant. This is the problem statement. Okay. So let us try to solve this. First of all, the moment fan type load is given, I should say for fan type load, TL is going to be proportional to omega square. This we had already written earlier when we were talking about the different types of loads in dynamics of load system chapter. We had already said fan type load. This is the truth. And another thing is that if the machine is running in steady state, TE should be equal to TL. This should be the case in steady state condition. So this is going to be true. So I should be able to say that if there are two torque situations we are talking about, so initially whatever is the case and subsequently or finally what is the case, let us try to write down everything. So initially I am going to have the series motor armature like this, and I'm going to have all four field coils connected like this. This is going to be the connection I'm going to have. But later on, when I'm looking at the connection, it is connected with two of them connected in series and these two groups connected in parallel. So this is the way it is going to be connected. So here I'm having VA. Here also I'm having the same VA. There is no difference. And if I call this current as 60 ampere, this is the first case, and this is running at 2000 RPM. And this is being coupled to a fan. The same way, in the second case, I don't know what the current is. Let me call this as I. And I'm going to have I by 2 and I by 2 going here. Okay. And here also it is coupled to the fan. So what we need to find out is what is the current value and what is the speed value. We don't know these two things. Okay. So this is what is given. So first thing I can write is because the resistance is negligible, VA is equal to EB because RA and RF are neglected. That is the reason why we are writing VA equal to EB. Even in this particular case, we are going to write the same thing. VA equal to EB. And EB is normally proportional to flux multiplied by speed. These two are going to be multiplied with each other to ultimately yield what is the back EMF. In this particular case also, we are going to have EB is the product of flux and speed. Now, in this particular case, if we assume each of them are having n turns, we are going to have 4ni as the MMF. Whereas we wrote earlier also, if you may recall, if I'm going to have n number of turns here, n number of turns here, n here and n here, I'm going to have 4n multiplied by I by 2. So I'm going to have 2ni as the MMF. So if I am saying in this particular case, the flux to be phi, and flux and current are proportional to each other, I can write this as I square, I multiplied by speed. Whereas compared to that, here the MMF is going to be half. So I should write this as I by 2 multiplied by omega. Right? So this is the way it is going to be. So this is one of the equations which correspond to the back EMF. So when I write that the back EMF is proportional to I multiplied by speed in the first case, in the second case, I have to write back EMF is proportional to I by 2 multiplied by speed. Okay. If I write what is the load torque, so I should write load torque 1, which is also same as TE1 in steady state. That is going to be proportional to flux multiplied by I. This is the product. The same way I should write TE2 is proportional to, again, flux multiplied by I. So in this particular case, flux becomes I by 2. Flux is proportional to I by 2 rather than I. So TE2 is going to be some K times I square by 2. Whereas here TE1 is going to be K times I square directly. So I should write this equation here as TE1 equal to K times 60 square. But this is also proportional to speed square because it is fan type load. So it is going to be some K dash multiplied by 2000 square. The same way I should be able to write here this one as K times whatever is I square divided by 2, but this will also be K dash multiplied by omega square. So I'm going to write basically these two equations. One is based on back EMF. The other one is based on the torque. So let me write these equations very clearly. EB1 equal to EB2, which is equal to, EB1 is equal to 60 multiplied by 2000. Okay, that is what is EB1. That is going to be equal to I omega divided by 2. So this corresponds to EB2, whereas this corresponds to EB1. And because we are neglecting the resistances, we can say VA and EB are one and the same, and VA remains as a constant. So this is equation number 1, from which I should be able to write I equal to 60 multiplied by 2000 multiplied by 2 divided by omega. So this is going to be the expression corresponding to the current. So this is new value of current I for the field connection, which is 2 in series in 2 parallel groups. So this is going to be the relationship between I and omega. So this is going to be equation number 1. So I can write this as 6 2s are 12, 12 2s are 24. So 24 multiplied by 10 power 4 divided by omega. Omega is in RPM in this particular case. And the next equation is going to be, so this is equation number 1. And equation number 2 is going to be TE1 divided by TE2, which is going to be 60 square divided by I square divided by 2. So that 2 can be taken up here, which is also incidentally equal to 2000 square, which is speed square divided by omega square. So this is going to be equation number 2. So you can substitute for I from 1 into 2. You can substitute for this, from which we should be able to get this as 60 square multiplied by 2 divided by I. We should be able to substitute this as 60 multiplied by 2000 multiplied by 2 whole square, and this can be omega square. Because it is I square, I'm substituting for I square, which is equal to 2000 square divided by omega square. So I should be able to write this as omega power 4 is equal to 2000 power 4 multiplied by 60 square multiplied by 2 square divided by 60 square multiplied by 2. Okay, so I can cancel this and this out, and I can cancel this and this out. So this is essentially omega equal to 2000 multiplied by 2 power 1 by 4. Okay, so this is going to be the speed what we get, and this comes out to be 2378 RPM. This is the speed what we get as the new value of speed. Now the current can be obtained from expression number 1, which gives us the current value. So the current value is 20 multiplied by 10 power 4 divided by omega. 24 multiplied by 10 power 4. So this is 24 multiplied by 10 power 4 divided by omega. Right? Okay. So have we substituted this correctly? 24 multiplied by 10 power 4 divided by omega. So I hope, yeah, so that is fine. So this is going to be calculated as 100 ampere. In fact, 100.9 ampere, 101 ampere roughly. So what we are getting in this particular case, the new current value happens to be 100.9 ampere, and the new value of speed happens to be 2378 RPM. So clearly, when you connect the field coils, 2 of them in series and both these groups in parallel, the speed increases. Originally, this was 2000 RPM, whereas now the speed has increased to 2378 RPM. Okay, and because the speed has increased, the torque will increase in the case of a fan. So obviously the current that is required in all probability will also increase. That is the reason why this case it was 60 ampere, whereas in this particular case it is 100.9 ampere. That's what we got now. So you should be able to roughly check whether the answer is correct or not just by reasoning in such a manner that if I am having all four field coils in series, the speed should be lower. The torque will also be lower because it is fan type load. Whereas when I'm connecting two of them in series and then the two groups in parallel, the speed should increase. If it so happens that you are getting a speed value which is less than 2000 RPM, then you know for sure that there is something wrong with your calculation. That's what I'm trying to get at. So you should be able to reason as to what will really be a correct answer, whether what you are getting as answer is correct or not. So that you should be able to reason. Okay, so we will look at discontinuous conduction in the next class, next lecture class.